So we've got this optimization problem where it says a manufacturer wants to design an open box having a square base and a surface area of 108 square inches, as shown in the figure right here. What dimensions will produce a box with the maximum volume? Now, they're asking for maximum volume, right? We're asking for maximum volume, but the only information they gave you was what? Surface area. The surface area, they want it to be how much? 108 square inches. Okay? So let's write what we know. We know that based on the figure here, okay, we know that the volume of a shape like this would be length times width times height. But if you look, the length and the width are the same, aren't they? They're x and x. And so your volume is going to be x times h. So your volume is x squared h. Okay. Now the problem is this has how many variables? 2. The volume's not really, I mean, yeah, it has 3, but in the part that we're going to take the derivative of, there's 2 variables right here. X and what? H. And so what we need to do is now we need to look at the equation in terms of surface area. And so right here in the problem, it tells us the surface area formula. Okay, so we know that the surface area equals x squared plus 4xh, and that equals, let me erase that portion. I don't like how they wrote right here. You can see they wrote equals 108, so they have an equals here and an equals here. We know that the surface area is 108, don't we? Okay, so in the place of the S right here, I'm going to put what? 108. So I've got 108 equals x squared plus 4xh. Now, can you see down here in my volume formula, I have an h? And do you see up here in this problem, I also have a what? If I were to solve the surface area formula in terms of h, then I could substitute it in for this h right here, couldn't I? And then I'd have an equation in terms of how many variables? Just one, right? In terms of x. Okay? So y'all go ahead and solve for h. So the first step in solving for h would be to subtract x squared on both sides. And so I'd have 108 minus x squared equals 4xh. And then I'll divide 4x on both sides. And so I have h equals 108 minus x squared all over 4x. Now, remember what I just told you. Okay? Even though they provide us with the surface area is 108 square inches. Even though they provide us with the surface area, we are maximizing the what? The volume. Okay? So we're saying we need the box to have a surface area of exactly 108 square inches, but we want to know what kind of shape could we make the box so that the volume is at its max. Now, the box may be a bunch of different shapes. Okay? It may be skinny and tall. It may be flat and wide. Okay? We're trying to make a box that will have the most possible volume and exactly 108 square inches of surface area. Okay? Now, if you think if you're a packager of, say, like a cereal box, you want to be able to hold the most inside the box you can and have maximum surface area for advertising purposes, right? And so this is a marketing person would do this exact, probably not the marketing person, probably the engineering person once the marketing person decides what their slogan or whatever is going to be. So is there any way that I can reduce 108 minus x squared over 4x? No. So let's go ahead and plug it in. And what we're going to do is we're going to plug it in for h right there. All right, so when we plug it in, we've got that the volume equals x squared times 108 minus x squared all over 4x. Okay? And now if you look at your problem, it's all in terms of what? X. And all we did was take what we solved for h and plug it into the volume formula that we manipulated at the beginning of the problem. And so now what we need to do is we need to simplify this. Okay? And so what I've got, and so x squared is understood to be over 1. So what I've got to do is I got to take this x squared and I got to distribute it on top. And so I've got volume equals 108x squared minus x to the what? 4 all over what? 4x. And then you notice on top, I can factor out what?
X squared.
Well, I can factor x squared out, but there's only one x on bottom that could possibly cancel with it, so I'm only going to cancel one of them. So I've got this equals x times 108x minus x cubed all over x. 4x, yeah, I keep just writing x. And then what cancels? This x cancels with that x. And so you've got volume equals 108x minus x cubed all over what? 4. So there's our volume formula. Okay, so now what I'm going to do is I'm going to maximize this formula right here. I'm going to maximize this formula. Okay, which means I need the derivative. I need to set the derivative equal to 0, and then once I know the critical numbers, I need to figure out which one's a maximum or a minimum. Now, the first thing I can do, though, is make this easier to take the derivative of. So I'm going to rewrite this formula, volume equals, and I'm going to take 108x, and I'm going to divide it by 4, and I'm going to take x cubed, and I'm going to divide it by 4. In other words, I'm splitting this into two terms that are easier to take the derivative of. What's 108 divided by 4?
27.
So I've got 27x minus x cubed over 4. Or I could write this as the volume equals 27x minus 1/4 x cubed. Okay, now we want to maximize this formula. This is the formula that represents our volume. We want to maximize it. Okay, now let's think of some things though. Our length can't be a negative number, can it?
No.
Okay, so if we get two critical numbers and one of them's negative, we're just going to throw that negative out. Okay, so let's take the derivative. Our dv over dt, because we're taking the derivative with respect to, dv over dx equals, what's the derivative of 27x? 27 minus 1/4 times 3 x to the second power. Right? And so I could rewrite that as dv over dx, because we're taking the derivative of the volume with respect to x, not t. I'm so used to related rates saying dt equals 27 minus 3/4 x squared. And now since we're maximizing that, I need to tell my critical numbers, don't I?
Yes. Make
Okay.
it equal to 0.
So I'm going to take my derivative right here, and I'm going to set it equal to 0. 27 minus 3/4 x squared equals 0. And the reason I'm setting it equal to 0 is I want to know where the slope of the tangent line equals 0. And so I'm going to add 3/4 x squared on both sides. Add 3/4 x squared on both sides. And so you have 27 equals 3/4 x squared, which then I'll divide 3/4 on both sides. Y'all type in your calculator what 27 divided by 3/4 is. And so as we keep working, 27 over 3/4 is 36, which equals x squared. And now I'm going to square root both sides, and when I do, I get x equals plus or minus 6. Now, as we think, our x represented in our image, okay, our x represented what? The length of the bottom of the box, right? So if you look at the box right here, okay, X represented the length of the bottom of the box right here. And so we know the length of the bottom of the box is not going to be a negative number. I know. So we have two critical numbers, but we know we can throw one out, right? Which one can we throw out? The negative, because you're not going to have a negative length to your box. So what I'm going to do is I'm going to draw my little number line, and I'm going to put 6 on it. And all I'm going to do is I'm going to confirm that at 6 there is a maximum and it's not a minimum. Okay? So what I want to test is I want to test what is f prime of what? 5.
We did 2, 0.
And what is, or we could do 0. Yeah, that'd work. Do 0. What is f prime of 0? And let's test f prime of 7. And the reason we are is we're testing to the left. When you plug 0 into the original function, into the derivative, what do you get?
Positive.
So the function is going up to the left. And then when you plug 7 in, do you get negative?
Negative.
So the function is going down to the right of 6. So that confirms that there's a maximum at 6. And so the box, when it has a length of 6 and a width of 6, has the maximum volume. Now, we need to calculate what the height would be, right?
Right.
3. Very good. And so what you know is that the maximum volume for this box would be if the base equaled 6, the width equaled 6, and the height equaled 3. Okay, so let's kind of wrap it up with a bow on this problem. So I love what the book says, and I never read the book to you, but I love what this says. In example 1, you should realize that there are infinitely many open boxes that have a surface area of 108 square inches. Okay, so the box could be this shape, or it could be this shape, or it could be this shape, all having the same surface area, right? Now the picture shows you that this first box has a surface area of 108, but the volume's 74 1/4. This one has a surface area of 108, but the volume's just 92. This one has a surface area of 108, but the volume is just what? 103. Okay, let's keep looking. Here are some other shaped boxes. Okay, all these also have a surface area of what? 108. But now the gold box that they have right here is the one we drew. Okay, it has dimensions 6 by 6 by 3, so we maximized it. Okay, we maximized the volume. Okay, because all 5 boxes they have drawn here have the appropriate surface area that we wanted, but all 5 of them have a different volume, don't they? Okay, so it says, to begin solving the problem, you might ask yourself, which basic shape would seem to yield a maximum volume? Should the box be tall, squat, or nearly cubical? Okay, you might even try calculating a few volumes, as shown in figure 3.54. That's what we're looking for, to see if you can get a better feeling for the optimum dimensions should be. Remember that you are not ready to begin solving the problem until you have clearly identified what the problem is. That's a great point. You know, you're not ready to solve the problem until you clearly understand what the problem's asking.
That's the hardest part.
That is the hardest part. And that's what's tough about word problems. Okay? You need to first evaluate what do they want to know from me before you start doing anything. Okay? So I thought this section of the book was really good. And that shows you right there that there's tons of different shapes that will all have the same surface area, but the gold one with the dimensions that we chose ended up having the maximum volume.